Thank you, everybody, for having me here to talk today at this awesome perfusion lecture. I've had the privilege of speaking here before, and it's fantastic. It's a great agenda, and this particular one on transplant, I think, is very relevant. The field is changing a lot, and there's a huge role for, obviously, perfusion being the cornerstone of a lot of the advancements that we do in transplantation. So this is very relevant. By way of disclosures, they're shown there. I received grant support for research from several entities that are shown there. The collaboration between the perfusion team and the transplant team has been integral to the success of our program and to the deployment of a lot of the ex vivo perfusion technologies that we've been doing here for some time now. And you know, we fly together with these teams, with perfusionists, handling a lot of the ex vivo work, and we recondition organs together. There's just so many different facets to this that wouldn't be able to do it without this collaboration. We also, as we speak, have a group of brilliant engineers right upstairs working on the next generation of ex vivo perfusion devices, also in collaboration with THI Perfusion School too, looking at extending the out-of-body time for organs beyond 30 hours now, even longer. They have a lung on the box now. It's been on there for 30 hours. So a lot of really amazing technology coming out. Today, I'm going to focus on advanced lung disease, which is the third leading cause of death worldwide behind cardiac disease. And it's once you have an irreversible state of lung disease, the only way to change that is to transplant the organ. But there's many challenges to getting an organ, not unlike cardiac transplant or heart transplant or lung transplant. There's about 15 to 30% of patients dying on the waiting list with this advanced lung disease waiting for an organ. And despite that, there's really only 20% of all of the donor offers that are sent to us at any given time are utilized for transplant. 80% of donor offers are actually turned down for transplant for a variety of reasons, whether it's age, distance, all sorts of different reasons why they're turned down. The standard donor criteria, what we all would love to see is shown here, the very clear chest x-ray, limited ischemic time, less than 6 hours out of the body, brain dead donor, less than 20 pack-year history of smoking, excellent blood gases, and age younger than 55. But unfortunately, that makes up a very small minority of the transplants that we're able to do. And I can tell you can count on one hand annually how often you get an organ like this. And yet we're doing somewhere 70 to 80 transplants. So how do we do that? Well, there have been a lot of reports about ways to extend different aspects of the donor criteria, such as increasing the ischemic time, such as using older age donors, such as using donation after circulatory death donors. So different ways to start to increase the donor pool. But even in these investigations, that increase has been very marginal, and it's been very limited because of the limitations of standard cold storage, where we can't evaluate the organ if it's in an extended criteria state. So ex vivo perfusion technology was first conceived of in 2001 by a gentleman by the name of Stig Steen, who took a DCD donor offer from a patient who suffered from a heart attack and put the donor lung blocks on a circuit. And he said that if a patient is dying of an acute MI, for them to serve as a donor, the lungs should be properly evaluated first on an ex vivo circuit before they're transplanted into a patient. So this was a very novel thought process. This was back in 2001, and it was the first publication of a donor organ being outside of the body and perfused and ventilated before it was transplanted. The standard ex vivo perfusion circuit is shown here. So basically, there's a chamber for the lungs. There's a ventilator that allows you to ventilate the lungs. There's blood pumping into the pulmonary artery, delivering oxygenated blood to the organ, and it drains out through the pulmonary vein. It goes into a reservoir. Then there's different gas tank mixtures that you can use to oxygenate the deoxygenator or the oxygenator that you're using, depending on whether you're trying to challenge the lungs and remove all oxygen from it, or if you're just trying to maintain it at rest mode, kind of like ECMO, with about 20% oxygen, just to provide basic oxygen to the organ while it rests. The alternative to doing this is an ice cooler. So ice cooler is the way we do pretty much all the other transplants, and you can get this anywhere, obviously, and you can just fill it with ice and you transport the organ like this. What is the literature behind ex vivo perfusion, and how does the data bear out? So I want to talk a little bit about this. One of the first reports came out of Toronto, and this was in about 2010 or so by Saipel and Kishabji. And they looked at 20 lungs that they put in an EVLP circuit. And they compared them to the standard procurement for very standard criteria donor lungs. And what they found was that there was really no difference in PGD. PGD is the way we grade the organ in the first 72 hours after lung transplant. So they really had no statistically significant difference between the lungs that were extended criteria on EVLP and those that were standard criteria donors on ice. And that was very encouraging and really paved the way for additional investigation. Unfortunately, the first multi-center series performed out of the UK could not really replicate that successful survival and graft dysfunction rate. And in fact, it was stopped prematurely because the EVLP arm had worse survival and higher graft dysfunction. Since then, there have been 2 devices that have been cleared by the FDA for clinical use in transplantation. And these are at various stages of clinical investigation. I'm going to share some of that with you. So the static EVLP platform is one that stays in your hospital. So the organ is actually brought over to you on ice, and then you instrument it into the device and evaluate it there. And sometimes it's even shipped back to another area to be transplanted, or it's transplanted in your own hospital. So it's a static EVLP platform. It's very much based on the protocol from the Toronto group, although it's a integrated circuit that is called the XPS system. The second option that is available is the one that we most commonly use now, which is the portable platform. It's a smaller circuit. It's about the size of a small George Foreman grill. You can rotate it through an ambulance, airport, plane, jets, anywhere. And it also has an integrated platform that houses the oxygenator, the pump, the sterile chamber for the lungs themselves. So looking at that first system, there really, interestingly, is not, ever since that one multi-center study, there hasn't been a published multi-center series on the XPS system yet. This is preliminary data that we saw at the International Society of Heart and Lung Transplant in 2022. It was a non-randomized prospective multi-center study. They included 200 EVLP lungs, 216 EVLP, and compared it to 116. They had about a 50% donor lung utilization. That means that 50% of the lungs were screened out on the EVLP circuit, on the static EVLP circuit. And the final results are still pending. But the initial results that were presented were pretty encouraging, that even with that kind of EVLP strategy, they still had a similar 1-year and 3-year survival by extending the organs using EVLP. Now, flipping over to the portable EVLP model, which is shown here, you can see that blood is being pumped into the lungs through the pulmonary artery. We're monitoring the flow, vascular resistance, and compliance through the Bluetooth connected monitor that we have. We're able to manipulate the flows, we're able to manipulate the temperature. We're able to identify changes in pulmonary vascular resistance or dynamic compliance. We can check oxygenation values before and after the lung. It really gives us a pretty comprehensive and continuous assessment of the organ from the time that it's procured at the donor hospital to the time that it's implanted here. So it's EVLP on wheels, but it's very consolidated. Another important difference with this protocol is it uses blood. And so this uses blood, red blood cells circulating through the circuit. compared to the static systems that use just actually high potassium, high dextran, clear solution with some albumin in it. So it's a little bit different. So now getting into some of the data behind it. So I will just preface this by saying that the data behind this portable system is actually pretty extensive. And now we've brought it out to 2 major publications, as well as long-term results, which I'm privileged to be able to disclose here today. So the INSPIRE trial was probably the largest randomized control study ever done in the history of lung transplantation, looking at donors. So actually randomized donors between coming on the OCS system or coming on the ICE group to see if there was non-inferiority or if maybe it was even better. This used standard criteria donor organs in this trial. So you can see in the control group, which was the standard ICE group, there were 165 patients. And in the OCS group, there were 141 patients. So what did the results look like? Well, number one, it proved that it was non-inferior. So for standard criteria donor organs, and that was really important to the FDA to be able to say that we have a safe platform that we can use. It doesn't injure the organ. So that was step one. But step 2 was to also look if there were some improvements in the graft performance and the graft function, even in the standard criteria donors. And in fact, there was. You can see nearly 50% reduction in the incidence of the severe primary graft dysfunction by using the OCS system to reduce the ischemic time from transportation going from point A to point B. How about the long-term outcomes of it? So we now have data out to 5 years, looking at the control group, the ICE group, compared to the OCS group. And what you can see at 5 years, there is a trend towards less chronic lung allograft dysfunction, which is defined as BOS. So there's better long-term graft function, although it was not statistically significantly different. So still, I think very important to prove that even in the long term, these graft lungs are still the same as what we would do normally in standard conditions. And patient survival, also bearing in mind that we're comparing these lungs that were transported for a significant amount of time compared to standard donor lungs on ICE, the long-term survival out to 5 years also was equivalent. So this tells us that we have a stable platform. It reduces early graft dysfunction. It may reduce long-term graft dysfunction, although that still has not been borne out. And you do have equivalent survival, and this is for standard criteria donor lungs. Then we switch over to the EXPAND trial, which was looking at extended criteria donor lungs. And in this trial, we perfused 93 extended criteria donor lungs. 87% of them met inclusion criteria. So that's a lot better than that 50% that I had shown you previously. This was very encouraging that we could actually recondition more of them than we otherwise would have. 79 of the lungs went to transplant. This gives you a layout of the types of extended criteria features that these lungs had. 39% were donors aged older than 55. 33% were from DCD donors. And just to remind the audience, if you don't know what DCD is, it's a huge pool of donors that we have access to where they're not yet deemed brain dead, but any further care is thought to be futile and they want to withdraw care. So when the family withdraws care, they just withdraw support. And if the patient expires within a certain period of time, which is usually about an hour, hour and a half, then the transplant team can then go and quickly open the chest and procure the organ. So that's a DCD donor. So 33% of them were DCD donors. 32% of them had longer than 6 hour expected cross-clamp times, and 25% of the donors had blood gases that were poor in the donor, and 27% had multiple criteria. There was 87% donor lung utilization, 13% were turned down, and the 1 year survival was actually better than we expected, even for a standard donor lung. So this was extremely encouraging, 91% 1 year patient survival. And then we look out further at the 4 year survival, and we see that the probability of developing BOS, which is bronchiolitis obliterans syndrome, that's basically another word for long-term graft dysfunction. So the probability of developing BOS was about 7.7% in the extended criteria lungs that were perfused on the EVLP in the OCS expand, compared to 15.9% in the Inspire group. And that was not statistically significant, but at 2 years and at 3 years, it was. So again, evidence that even long-term, these lungs are performing very well. And there certainly seems to be at least a trend towards better long-term outcomes than even with the standard criteria donor lungs. This looks at the overall survival, comparing so-called worst case scenario, which is extended criteria donors in red that were transported for long periods of time on the device, compared to blue, which is standard criteria donors transported on ice in the Inspire trial. And the survival was equivalent across the board out to 5 years. So this was very encouraging and gave the transplant community confidence to continue to use extended criteria donor organs with the system. Now, where is it going? Where are we going to from here? This is obviously opening a lot of possibilities, a lot of opportunities, some of which deal with pharmaceutical reconditioning of the organ on these device platforms that we now have, different strategic ways to recondition the organ. But also the more obvious and intuitive thing is that it opens the door to longer distance donors. So we can actually travel much farther now. We can consider national organ perfusion systems, which is what's actually happening right now. They've developed about close to 20 different pods throughout the United States where they fly out the organ to the center. If the center doesn't have a procurement team or doesn't have the resources to go out to like Hawaii, for example, they have a pod there and they'll deliver the organ to you on the OCS device. So this is an interesting program that's currently under development. And we're actually involved in helping to guide some of those efforts. And you can see the different distribution that currently exists for using this technology. The static EVLP systems are also being used in this capacity. There's about 2 or 3 main hubs where organs are sent to that hub. They're reconditioned through a variety of different maneuvers, and then they are sent back, but they're sent back on ice. So I think the data for that is still pending for us to understand how that pans out. But initial conceptual design seems interesting. So how are we currently using this technology here at Baylor St. Luke's? So we're very early adopters. We've been using this for about like 10 years now, since its infancy, since the early trials, and we're integral in developing a lot of the data that I just showed you. So we've become comfortable with it. With our perfusion groups, we travel very far distances. While normally you have about a 250 nautical mile, we go out to 500, or we even, quite frankly, go anywhere in the continental US with the device without any concerns for time. If you look at our runs, the out-of-body time, remember that I said 6 hours was the limit for standard criteria donors. In our OCS runs, 6 hours is the minimum that we do. So we actually go out as far as even 20 hours, 22 hours out of body. So substantial expansion of the amount of time that the organ is spent out of body. And the perfusion times on the box are also pretty extensive, ranging anywhere from 3-4 hours on the box to as much as 17-18 hours on the box. We also take advantage of this so that we can keep one lung perfusing on the device while we start to implant the other lung. And that gives us a lot of time, because each dissection on the left or the right side can be 30 minutes or it can be 3 hours, depending on whether it's a redo or whether it's really stuck. So having the ability to keep that other lung ventilating and perfusing opens up some options. We've done other things like taken biopsies. We've reconditioned with different antibiotics. There's just an enormous assortment of different things that you can do to assess and recondition and transport the organ with this kind of technology. Despite using it for very long distances and extended donors, our outcomes have been excellent, and in fact have been better than our experience with standard ice preservation, even here in our own center. And there's a huge discrepancy when you look at the out-of-body times for our OCS groups versus our standard ice. It's night and day, but despite that, we still have the same, if not better, survival short and long term. We're doing a lot of interesting biomarker studies here in collaboration with the Texas Bar, where we're looking at different cytokine signatures, exosome signatures, to identify which patients are potentially more likely to develop graft dysfunction after the organ is implanted. We even are using tissue samples at times to give us even more detailed genetic fingerprinting. Right now, upstairs in the regenerative medicine department, they have an organ on this new device that is now going on 30 hours, where we're able to manipulate different temperature flow sensors, different flow rates, different perfusion pumps, different methods to try to improve the organ. So we have actually, this is the older version of it, but now it's very consolidated, pretty slick. Ultimately, we want to try to really recondition lungs that don't just need a little bit of help, but lungs that really otherwise were completely not transplantable, such as this one. So this is an animal model. This is an animal DCD model that we had, where the animal was extubated and then died. And actually was, this is, obviously IRB approved protocols. We're down for 2 hours. And this mimics an out of body cardiac arrest. So someone is not even in the hospital. So the lung was down, the whole body was down for 2 hours, which is really, really long. Nothing that's done clinically right now. So we recovered the organ after 2 hours, placed it on the device. You saw how stiff it looked, but over time, here you can see as blood is pumping through it and draining out of it, with gentle conservative ventilation, use of whole donor blood. So we use the blood from the animal itself. Little by little, the lung starts recruiting its different segments. You see the inferior lobe, middle lobes expanding, upper lobes expanding. By the time we got to 8 hours, the blood gases were getting better. The pulmonary vascular resistance was getting better, pulmonary pressures. And by the time we got to 24 hours, it was almost indistinguishable to a standard criteria swine lung in this case. So this is kind of the area that we want to try to start to move towards, is using this type of technology to go even further to try to rescue more organs and more scenarios than we otherwise could. So I just want to thank everybody for allowing me to present today, and thank our transplant teams, all of our investigators, data analysts, just a slew of different individuals and programs that support all of this enormous amount of research that's going on. So thank you so much, and I'm happy to take any questions.